The second discussion is, let's go back to here. We finish this discussion and know the Wronskian. Now for the second order linear equation, we actually can, for given two linearly independent solutions, we can calculate the Wronskian just using this method. Now this Wronskian. As it turns out, it just will be mostly independent of the choice of your solution, and the choice of solution will affect only the constant in front. The functional form of the Wronskian will be the same. So you have y sub 1, y sub 2. You have two linear independent solutions. You have y sub 1 pi, y sub 2 pi. Right? And then we can solve for the Wronskian given by this equation. Now, do you know how to do that, or do you know how to proceed? Right? Anyone, any suggestion? Yeah, given by this form. And what do you do now? Well, this is the determinant of what to do to solve for Wronskian. Right. First, the easiest way is just find a differential equation of W for W, right? Because you already have a differential equation of Y. Now you want a differential equation for W. So you need the W pi. Yeah, W pi. What is W pi now? Given by this. Yeah. So first you take the derivative over this first row, right? And then the second term is taking the derivative over the second row. Well, we talked about that before in last semester, right? Yeah. You remember I talked about that in last semester, right? So this is generally for all rank of matrix. That doesn't just by 2 by 2. 2 by 2 is too easy. You don't have to do that. You have higher rank. You just do it. Say if you have a fourth order, fourth rank, you have 4 by 4 matrix. It determines your 4 row and 4 column, right? And you can either do it by row or by column. By row is taking the derivative is your 4 terms. The first term is derivative over the first row. The second term is derivative over the second row, and so on. You have 4 terms. It's just this is just you will just think about it, it's just the usual rule of taking the derivative of products of function. That you can see that is the correct way to do it right away. All right. Now this one is 0, just like what we did over there, right? 0. And this one is similar to that discussion, right? So we can write it like just like what we did here, minus p y1 y2 y1 pi y2 pi plus minus q y1 y2 y1 y2, just like what we did here, because you just express double pi in terms of the other two, and you get this too, right? You see that, right? Just right away. And now this one is just 0, just like what we did over there. And for this one, you identify this just the same Wronskian. So this is minus PW. Is that okay? Now you found a differential equation, which is a simple one. The first derivative, W pi is minus P, which is a function of X. We generate a function of X times W. You can solve it right away because of the simple nature of this equation. It's just by it, it's separable, and then you can just integrate it out. So W will be given by a certain constant. The textbook calls W. I think W at a certain A or something like that. Exponential of, because it's minus P, so you're really good. Or you can take the minus sign here, X, and you start with A or something. I think that was the textbook. Yeah. Yeah. That is your solution, right? So your choice of the y1, y sub 2 will only affect this constant because this is the same. This is just the p function in the equation. This doesn't matter. Whatever solution, you still have the same p. And this a is just your choice of where you start to integrate. So the choice of your solution and the choice of this lower limit is given by, will affect only the constant in front. Otherwise, it's the same form. This exponential function of this integrating over this, the p parameter. Is that okay? So that's the solution. Is that okay? That's derivation.